Lesson 12.2, Geometric Sequences. How can you define a geometric sequence algebraically? Well, like we did with the arithmetic sequence, you can two ways. One, you can do it explicitly. And that would be f of n equals a times r to the n, or you can do it recursively. That don't look good. That don't look good. Recursively, and that would be f of 0 equals a, and then f of n would equal f of n minus 1 times r. And we'll define a and r and such during the lesson. Investigating geometric sequences. As a tree grows, limbs branch off the trunk. Then smaller limbs branch off these limbs, and each branch splits off into smaller and smaller copies of itself, the same way throughout the entire tree. A mathematical object called a fractal tree resembles this growth. Start by drawing a vertical line at the bottom of a piece of paper. This is stage 0 of the fractal tree and is considered to be the one branch. The length of this branch is defined as 1 unit. For stage 1, draw 2 branches. For stage 1, draw 2 branches off of the top of the first branch. And this would be here, that would be stage 2, and that would be stage 2. For this fractal tree, each smaller branch is half the length of the previous branch and is at a 45 degree angle from the direction of the parent branch. The first 4 iterations, stages 0 through 3, are shown. So this is stage 0, stage 1, stage 2, and stage 3. In stage 2, there are 2 branches drawn at the end of each of the 2 branches drawn in stage 1. So that would be here, that would be this one, and that one, and that one. There are 4 new branches in stage 2. Each one of these branches is half the length of its predecessor, or 1/4 unit length. Remember, this first one here was 1/2. This is 1/2, and that's 1/2 of that, so that would be 1/4. For stage 3, there are 8 new branches. For stage 3, 8 new branches in total. To draw stage 4, a total of 16 branches must be drawn, and to draw stage 5, a total of 32 branches must be drawn. Thus, each stage adds 2 times as many branches as the previous. So stage 3, you've got here and here, there and there, and there and there, and there and there. So that's stage 3, and then I can't draw stage 4 and 5. Complete the table. Stage 0, 1 branch. Pattern is 1. And new branches would be 2 to the 0. Well, 2 to the 0 power is 1. Stage 2, 2 times 1, 2 to the first power. Stage 2, 4. 2 times 2, so that's 2 squared. Stage 3 would be 8, or 2 times 4, which is 2 to the third power. Stage 4 is 16, and that's 2 times 8, or 2 to the fourth power. Stage 5 is 32. That would be 2 times 16, which is 2 to the fifth power. And stage 6 would be 64. That would be 2 times 32, which is 2 to the sixth power. Are we seeing a pattern here? The procedure for each stage after stage 0 is to draw 2 branches on each branch. 2 branches on each branch. Using the description above, write an equation for the number of new branches in a stage given the previous stage. Let's represent stage S as n sub s, and stage 3 will be n sub 3. So n sub 4 is 2 times n sub 3, and then stage 5, n sub 5 would be 2 times stage 4. N sub 6 would be 2 times n sub 5. And then, okay, so n sub s would be 2 times n sub s minus 1. Rewrite the rule for stage S as a function of n sub s that has a stage number as an input and the number of branches in the stage as an output. That would be 2 to the s power. Recall that the domain of a function is a set of all numbers for which the function is defined. N sub s is a function of s, and s is a stage number. Since the stage number refers to the number of times, the tree has branched, it has to be whole numbers. It has to be whole numbers. Write the domain of n sub s in set notation. So s such that s is a whole number. Similarly, the range of a function is a set of all possible values that the function can output over the domain. Let n sub s equal b, the number of branches, of new branches. Number of new branches. The range of n sub s is 1, 2, 4, 8, 16, 32, and so on. The range of n sub s is n such that n equals 2 to the s power, where s is it's a whole number. Graph the first five values of n sub s on the axis provided. The first value is graphed for you. I seem to be having some issues here. All right, graph the first five values of n sub s. So let's see, 0, and then 1 would be 2. 2 would be 4. 3 would be 8. 4 would be 16. And then 5 would be 32, and it's not on here. As S increases, N sub S increases. There's something going on with my computer here. It is doing something. I guess Windows is downloading something or something. I don't know. Increases. All right. N sub S is an increasing function. Complete the table for each branch length. Let me just get that up a little bit more. Complete the table for each branch length. Well, let's see. 0, number of branches is 1. Branch length is 1 unit. Stage number 1, the number of branches, well, that was 2 off of it. And the branch length was 1/2. Stage 2, the number of branches was 4. And the branch length was 1/4. Stage 3, the number of branches was 8. And the branch length was 1/8. Stage 4, the branch length or the number of branches was 16, and the branch length was 16. 5, the number of branches was 32, and the branch length was 1/32. And if you'll notice, there's a pattern here. L sub S, write L sub S expressing the branch length as a function of the stage. So L sub S equals 1/2 to the S power. Write the domain and range of L sub S in set notation. The domain of L sub S is S such that S is a whole number. Whole number, that's already written. Whole number. The range of L of S is 1, 1/2, 1/4, 1/8, 1/16, 1/32, and so on and so on. The range of L of S is L such that L equals 1/2 to the S, where S is a whole number. Graph the first 5 values of L of S on the axis provided. The 5th point has been graphed for you. So this would be 2 to the nth power. All right, so 0 was 1. 1 was 1/2. 2 was 1/4. 3 was 1/8. So that would be half of that. And then 4 would have been 1/16, and that's marked. And then 5 would have been down here, even half that. So as L increases, L of S decreases. So L of S is a decreasing function. Reflect. What is the total length added at each stage? What is the total length added at each stage? Well, the number of new branches times the length of each branch. N of S times N of S, N of S times L of S, which should be 2 to the S power times 1/2 to the S power. Which that equals 2 to the S times 2 to the negative S, which is 2 to the S minus S, and 2 to the S minus S is 2 to the 0, which is 1. Is the total length of all branches a sequence? If so, identify the sequence. I'd say yes. And the sequence would be 1, 2, 3, and so on, S, and so on. Writing explicit and recursive rules for geometric sequences. A sequence is a set of numbers related by a common rule. All sequences start with an initial term. In a geometric sequence, the ratio of any term to the previous term is constant. This constant ratio is called the common ratio and is denoted by R, such that R cannot equal 1. In the explicit form of the sequence, each term is found by evaluating the function f of n equals a times n to the nth power, or f of n equals a times r to the n minus 1 power, where a is the initial value and r is the common ratio for some whole number n. Note that there are two forms of the explicit rule because it is permissible to call the initial value the first term, or to call a times r the first term. A geometric sequence can also be defined recursively by f of n equals r times f of n minus 1, where either f of 0 equals a or f of 1 equals a, again depending on the way the terms of the sequence are numbered. F of n equals r times f of n minus 1 is called the recursive rule for the sequence. Now, go ahead and stop the video and take a second and look at A. And when you come back, we'll write the explicit and the recursive rules for B. Glad you're back. You got 1 and then 1 over 25, 2 over 1/5, 3 over 1, 4 matches with 5, 5 with 25, and so on and so on. Determine A and R, then write the explicit and recursive rules. Find the common ratio, f of n divided by f of n minus 1 equals R. Now, if you look here, this would be a good one to do, okay? And that would be f of 4 equals 5, and f of 3 equals 1. So now you got 5 divided by 1, which is real easy, 5. You can use any of them. It doesn't matter. And I'll show you what I mean. We'll do f of 5 equals 25. And then f of 4 equals 5. Well, 25 divided by 5 is 5. So, like I said, it doesn't matter which one. I just chose those two because it was kind of convenient. Find the initial value a equals f of 1 from the table. Well, f of 1 equals 1 over 25. And that's your a. Find the explicit rule f of n equals a times r to the n minus 1. So f of n equals 1 over 25 times 5 to the n minus 1. Write the recursive rule. Write the recursive rule. F of n equals 5 times f of n minus 1, where n is greater than or equal to 2, and f of 1 equals 1 over 25. The explicit rule is 1 over 25 times 5 to the n minus 1 power. And the recursive rule is f of n equals 5 times f of n minus 1, where n is greater than or equal to 2, where f of 1 is 1 over 25. Reflect. If you were told that a geometric sequence had an initial value f of 5 equals 5, could you write an explicit and a recursive rule for the function? Well, yes. Yes, you could. What would the explicit rule be? F of n equals 5 times r to the n minus 1. And that would be 4 some r. Your turn. Write the explicit and recursive rules for a geometric sequence given a table of values. So you could stop the video and take a second, work it on yourself. All right, glad you're back. So what do we need? The equation is f of n equals a times r to the n minus, well, that would just be n this time here, since we're starting with 0. So we'll just put an n there. What do we need to know? Well, we need to find the a, when f of 0 equals a, which is 1 over 27. So that's our a. We need to find our r. Well, our r is, and then I'm going to choose these two right here. Okay, so that's going to give me f of 4 over f of 3, which is 3 divided by 1, which is 3. So my r is 3. The explicit formula, or explicit rule, however you want to say it, f of n equals 1 over 27 times 3 to the nth power. Recursive, the recursive rule would be f of 0 equals 1 over 27, and f of n would be 3 times f of n minus 1, for n is greater than or equal to 1. Well, let's try 5. Go ahead and stop the video for a second and try it on yourself. Try it yourself. All right, glad you're back. We still need to find A, which in this case is f of 1, and f of 1 is 0.001. R, and this time I'll use these two right here. I've got f of 5 over f of 4, which would be 10 over 1, which is just 10. All right, explicit formula. Now this formula is going to be a little bit different than the other one because we're starting at 1. So we're going to have f of n equals 0.001 times 10, and instead of just n, we're going to n minus 1 so that it can't go to 0. Recursive, the recursive one would be f of 1 equals 0.001, and f of n would be 10 times f of n minus 1. N is greater than or equal to 2. All right, good. Graphing geometric sequences. To graph a geometric sequence, give an explicit or a recursive rule. You can use the rule to generate a table of values and then graph those points on a coordinate plane. Since the domain of a geometric sequence consists only of whole numbers, its graph consists of individual points, not a smooth curve. So example 2, given an explicit or recursive rule for a geometric sequence, use a table to generate values and draw the graph of the sequence. So A is done for you, and take a second and review it. Stop the video and review it, and then come back and we'll do B. All right, glad you're back. Recursive rule, f of n equals 0.5 times f of n minus 1. All right, so we got 0, 1, 2, 3, 4, 5, 6. If f of 0 is 16, f of 1 would be, well, let's see, 0.5 times 16, and that gives you 8. F of 2 would be 0.5 times 8, which is 4. F of 3 would be 0.5 times 4, which is 2. And then 0.5 times 2 would give you 1. 0.5 times 1 would give you 1/2. 0.5 times 1/2 would give you 1/4. So let's graph these. If 0 is 16, we'll put that right there. 0 is 16. 1 is 8, and that would be right there. 2 is 4, so 2 is 4. 3 is 2. 4 is 1. 5 is 1/2. 6 is 1/4. And it'll get closer and closer to this x-axis, but we'll actually never touch it. Your turn. Number 6. Given either an explicit or recursive rule for a geometric sequence, use a table to generate values and draw the graph of the sequence. So number 6. What kind of a rule is that? I believe that's an explicit rule, right? Explicit rule. So what are we going to do? Well, we're going to put this 1 in. 1 minus 1 is 0. 2 to the 0 is 1. 3 times 1 is 3. And we'll just, let's see, f of 1 equals 3 times 2 to the 1 minus 1, which is 3 times 2. 1 minus 1 is 0. Well, 2 to the 0 power is 1. 3 times 1 is 3. F of 2 would be 3 times 2 to the 2 minus 1, minus 1. Poor penmanship again. 2 minus 1. 2 minus 1 is just 1, so that's 3 times 2 to the first power, which is 6. So we'll put a 6 here. F to the 3 would be 3 times 2 to the 3 minus 1, or 3 squared. 3 times 3 squared. Let's do that. F of 3 equals 3 times 2 to the 3 minus 1. I'll see, I was about to mess that up. 3 times 2 squared, which is 4. That gives you 12. All right. F to the 4 is 3 times 2 to the 4 minus 1, which would be 3 times 2 to the third power. 2 to the third power is 8. 3 times 8 is 24. And let's see, F of 5 will be 3 times 2 to the 5 minus 1, which is 3 times 2 to the 4th. Well, 2 to the 4th is 16. 3 times 16 is 48. So let's graph these. How does it graph? So 1 gives you 3, right? And then 2 gives you 6. 3 gives you 12. And then 4, well, that's off the charts. Number 7. Number 7. F of n equals 3 times f of n minus 1. Well, f of 1 is 2. This is what you call a recursive. This is a recursive. The other one was explicit. This is one. How can you tell? Well, first it gives you the first term there. And then, 2 minus 1 would be f of 1. So that would be, let's see, f of 2 would be 3 times f of 2 minus 1 would be f of 1. And f of 1 is 2, so that's going to give you 6. 3 times 2 is 6. F of 3 would be 3 times, 3 minus 1 is 2. F of 2, which would be 3 times 6, and that gives you 18. F of 4 would be 3 times f of 3, which is 3 times 18. I think that's 54. And then f of 5 would be 3 times f of 4, which is 3 times 54. And I get 162. But we don't have to graph all of these. 1 gives you 2. 2 gives you 6. 3 gives you 18, and that's as far as we can go on that. The rest is off the chart. Modeling with a geometric sequence. Given a real-world situation that can be modeled with a geometric sequence, you can use an explicit or a recursive rule to answer a question about the situation. Right? Both an explicit and recursive rule for the geometric sequence that models the situation. Use the sequence to answer the question about the situation. A, let you read, well, let's see. I guess we kind of got to do this one together. The Wimbledon Ladies Singles Championship begins with 128 players. Each match, 2 players play and only one moves to the next round. The players complete until there's one winner. How many rounds must the winner play? Identify the important information. The first round requires, if there's 2 people playing in each one, that would be 128 divided by 2, which gives me 64. So the first round requires 64 matches. So A equals 64. The next round requires half as many matches. So R equals 1/2. Formulate a plan. Let N represent the number of rounds played, and let F of N represent the number of matches played at the round. Create the explicit rule and recursive rule for the tournament. The final round will have 1 match. So substitute this value into the explicit rule and solve for N. Solve. The explicit rule is, well, what is our A? Our initial value, that was 64. What is our R? Well, that's 1/2. So we're going to have 64 times 1/2 to the N minus 1, for N is greater than or equal to 1. The recursive rule is F of N equals 1/2 times F of N minus 1, where N is greater than or equal to 2, and F of 1 is 64. The final round will have 1 match, so substitute 1 for N, F of N into the explicit rule and solve for N. So if F of N equals 64 times 1/2 to the N minus 1, and F of N is 1, the final match is 1, we have 1 equals 64 times 1/2. Well, let's divide both sides by 64, and you get 1 over 64 equals 1/2 to the N minus 1. To solve this, we're going to have to do this 1 over 64. We're going to have to make, so that would be, we need to get the same base like we got here. So that would be 1/2 to the 6th power equals 1/2 to the N minus 1. So 1/2 to the 6th power equals 1/2 to the N minus 1. So now we have the same base. 2 powers with the same positive base other than 1 are equal if and only if the exponents are equal. So we can get rid of the bases, and that gives us 6 equals N minus 1. So we're going to add 1 to both sides. We're going to add 1 to both sides. 6, so 6 equals, add 1 to both sides, so N equals 7. The winner must play in 7 rounds. Pretty cool, huh? Add and evaluate, justify and evaluate. The answer of 7 rounds makes sense because using the explicit rule gives F of 7 equals, and that would be 1. And the final round will have 1 match. This result can be checked with using the recursive rule, which again results in F of 7 equals 1. So we'll put a 1 here and a 1 there. Write both an explicit and recursive rule for the geometric sequence that models the situation. Use the sequence to answer the questions asked about the situation. A particular type of bacteria divides into 2 new bacteria every 20 minutes. A scientist growing the bacteria in a laboratory begins with 200 bacteria. How many bacteria are present 4 hours later? Well, what do we know? Well, your N is going to be in 20-minute increments, so you're going to have 1, 2, 3, and so on, right? So let's define that. N equals the number of 20-minute batches. Okay, that's going to be real important when we try to figure out how far 4 hours is. All right, so what do we got here? R, what is a, let's see, uh, well, R equals 2. Bacteria double, it said, let's see, particular divides into 2. So that's our R. And this is a scientist growing the bacteria begins with 200 bacteria. So A equals 200. Do we? Well, I think we got everything. So an explicit formula, let's see, explicit would be F of N equals A times R. And since we're doing time, we're going to just do, we'll just do N. And then N is greater than or equal to 0. So 4 hours. Let's see, 4 hours. How many 20 minutes? So there's 3 20-minute in each hour. So 3 times 4, that would give you 12, right? So F of N equals A times R to the N. So A is 200 times 2 to the 12th power. And I'm going to need a calculator for that. So we've got, let's go to calculator. 200 times 2 caret, and that was 12. There was 12 20-minute sections in 2 hours. So that's going to give me 819,000, or 819,200. So F of 12 equals 819,200. Now, how would we do that recursively? I think we'll just do the recursive formula. Recursive. So we're going to have F of 0 is 200. At time 0, we had 200. And then F of N equals 2 times F of N minus 1. And that's for N is greater than or equal to 1. Because remember, we started at 0, F of 0. So N is greater than or equal to 1. Pretty cool. That bacteria stuff grows fast, don't it? Number 9, describe the difference between an explicit rule for a geometric sequence and a recursive rule. Well, an exclusive rule allows you to compute any value directly. And explicit rule, and that's the same as it was for an arithmetic sequence. An explicit rule allows you to compute any value directly. And even with a geometric sequence, a recursive rule, it kind of builds on the previous one. It allows you to compute a value from the previous value. All right, number 10. How would you decide to use n equals 0 how would you decide to use n equals 0 or n equals 1 as a starting value for n for a geometric sequence modeling a real-world situation? Personally, I think the only time I use n equals 0 is, something that, a time-based uh, a time-based function would be the only time I would really use 0. Number 11, essential question check-in. How do you define a geometric sequence in an algebraic way? How do you define a geometric sequence in an algebraic way? Well, either explicitly or recursively. Explicitly, f of n equals a times r to the n if you're starting at 0, or f of n equals a times r to the n minus 1 if you're not. Recursively, f of 0 equals a, or f of 1 equals a, and then f of n equals f of n minus 1 times r for n is greater than or equal to 1. And folks, that concludes lesson 12-2. Enjoy your evening and see you tomorrow in school.